All right, so now we're gonna start really getting into like the what I call, I guess, the meat and bones of this chapter, the meat and potatoes, in other words. So like really what this chapter is all about, and that is regression lines. Regression lines. Now, don't worry too much about the name because you're like, what regression line? What does that even mean? There's a technical meaning which I'll talk about later, but it's actually not too important. What the real idea that you need to understand is that we like to use regression lines in statistics because they are simple equations. And the simpler an equation is, the easier it is for, statisticians, no matter how smart they are, and normal folks, to understand the data. So, by simple equation, we mean a straight line equation. These are the typical equations you'll learn in like algebra, the y equals mx plus b. We'll see it in a different form, which is the a plus bx form. So we're gonna have y hat. This is actually a hat. It kind of looks like a hat. If the y was a person or well, whatever it is, it's a hat. So y hat equals a plus bx. Now this y hat stands for predicted y, and that's going to be a big deal, especially on your AP exam. Don't just think you can't leave that y without that hat. You got to make sure they got the hat on them, because if you don't, you actually will lose points off. And I tell my students this because I'll mark points off of them too, because they're really strict about this. So y hat equals a plus bx. And the reason we like linear equations is because, again, they're easy to work with. They're straightforward. So if we can basically describe the relationship between two variables in a simple manner using this equation, that'll be great. So this is always our goal, to try to find a possible way to describe the relationship between two variables with a regression line, or, again, a linear equation. So breaking it down, this is the y hat symbol, and that means the predicted value of y, the value we would get for y for a given x value. In other words, remember, we also call the response variable, and we call, x the explanatory variable. The b is still the slope. And just like in algebra, it represents the change in y over the change in x. But also we have to be sure to understand what it means in context. So we're going to be going over some examples and we'll break it down, but again, keep the context in a sense. This is all that is saying. How much we think y is predicted to change when x changes by 1. Now, a is going to be the y-intercept, just like in algebra, except, it's a different letter. That's just the way it is. That's just the way, and statisticians will write these equations. So you got to get used to it, because your graphing calculator, it'll be that same form on your formula sheet. It'll be that same form, no big deal. But that's the y-intercept. In other words, the value of y that we will predict when x is equal to 0. So again, this is basically a mathematical description. We like to say it's a way to describe or explain the relationship between x and y. Now, residuals, which we're going to talk about a little bit later, but let me just touch on it now. It's basically going to be the difference between our guess and the actual value of y. So the residual is equal to the actual value of y minus predicted value of y. And again, I'll go back to this in a bit. So I'm going to first jump so we can go over this first part. Then we'll focus on the residual. So let's go through an example of how we can use this regression line for problems that we're going to be doing in stats. All right, so here we got some data dealing with packaging cardboard, square inches. And this company is trying to make, cereal, and they're packaging it in cardboard. Makes sense? And they're gonna have different sizes, because they're gonna have bigger boxes of cereal for family size, or just those weekend college kids or whatever. So different sizes. The bigger the box, the more weight that the box can hold, the bigger the cereal. So here's our data. So we're going to plot this and we're going to describe it. So first, let's make sure we understand what would be our exclamatory variable and what would be our response. And yeah, you might have guessed it, the packaging cardboard is going to be our exclamatory variable because, the amount of cardboard we have is going to lead to us being able to have more cereal. So let's make a scatter plot with packaging cardboard on X and the weight of the cereal on Y. So bang, here we go. Make sure you always label your axes with the variable, so packaging cardboard, in square inches, and the net weight of the cereal. And we're going to describe the data, and we have to be very specific in what we address. And that is, we have to make sure we address the direction, form, strength, and any outliers. That's key on your AP exam because they're going to actually grade you based on those 4 criteria, and it's not going to tell you specifically. So we were basically going to say there appears to be a positive, linear, looks like pretty strong relationship between packaging cardboard and net weight of cereal with no obvious outliers. So here we are, bang. And I'm going to put checks by the 4 things we have to mention. So remember this stuff, the direction, the form, strength, any outliers. Those 4 things, make sure you mention them. Remember the DOFs, DOFs, D-O-F-S. Direction, outliers, form, strength. Now, we're going to plot the line, y equals negative 132.1 plus 2.29x. And it gives us, what the x is, the x explanatory variable or the amount of packaging cardboard, and y is the net weight of the cereal in grams. So don't try to plot this by by the slope and the y-intercept. Just pick 2 points that this line goes through. Pick 2 points far apart. Sometimes I'll have my students will want to use the slope and go up. That's going to be very tedious and it's not going to come out right when it's that small. So I just basically calculated what the y values were when x was 100 and when x was 500. So I found that when x is 100, that y was about 96.9, and when x was 500, y was 1012.9. So it goes through these 2 points. So what I do is I just plot those points, and draw my line through them. About right there. You actually put pink and 500. All right. Now, let's see what these people want. It says, tell the executives how much cereal a new experimental green package that uses 200 square inches of cardboard is expected to hold based on your equation. So again, let's recognize what the purpose of this equation is. It's to give us predicted values of y, in this case, predicted values of the weight of the cereal that will hold based on a specific amount of cardboard that you're given. So if we're given 260, in other words, 260 for x, to find y, we just plug in 260 for x into here and just calculate y. So then y will just be negative 32, or nope, negative 132.1 plus 2.29 times 260. And just let your calculator do the math. And you're going to get, it's going to expect it to hold about 463.3 grams. All right, now part D, interpret the meaning of the slope and the y-intercept in the context of the problem. Does this y-intercept make sense in the context of the problem? Okay, so the slope is this 2.29. Now, what that means, or what that means in context, is that as the X value, or as the packaging cardboard increases by 1 square inch, we're expected to, or we're going to expect to have the amount of cereal that can be held, or the weight of cereal, to go up by this amount. So for each additional inch of packaging cardboard, the net weight of cereal is predicted to increase by 2.29 inches, or sorry, predicted to increase by 2.29 grams. Remember, let me just kind of break it out so that some of this, remember the slope is slope is 2.29 over 1. Remember, that's the change in y over change in x. If you want delta y over delta x. And the delta y in this case is at 2.29. So that change in grams, you think of it change in grams over the change in packaging cardboard, or square inches, I guess, square inches of cardboard. I'm gonna write completely in a minute, but let's go over the y-intercept. The y-intercept would be the negative 132.1, and that's basically saying that when there's no packaging cardboard, you're expected to hold negative 132.1 grams of cereal in the box, which makes no sense, obviously. All right, so then now part E, what's the residual for the 471 square inch box? Draw this residual on your scatter plot. Okay, so going back to what residual means. So the residual is gonna be the difference between your predicted y value and the actual y value from the data. In other words, when you're using your least squares regression line, or your regression line, or whatever line you're going to use to predict, you're not always going to be right. Your guesses aren't going to be exactly correct. That'll be great if it were, but the real fact is that these are guesses, and sometimes you're going to be off more than others, that depending on what the values are. So these differences are the residuals. Think of residuals like in everyday context, like the leftover. So the equation is equal to the actual y minus predicted y. Remember APS, that's kind of a good way to remember it. The residual is the actual y minus predicted y. So let's look at what's going on here. So we want to figure out what the residual is for the 471 square inch box. So we need to figure out what the actual and predicted y value are. So actual y would just be y minus y hat, actual minus predicted. So if we look at the data we got here, the 471 square inch box has an actual y value of 1020 square inches, or 1020 grams. So it'll be 1020 minus the predicted y value, or the value that you would get when you would plug in 471 into x in the equation. Remember, this is your equation for predicted y. So for that, you want to then calculate what the y hat would be. So in this case, y hat, use your equation that we got, the 132.1 plus 2.29 times 471 And you get 946.49. So we're going to have this be our predicted. So 1020 minus 946.49. And we'll get 73.51 grams. 73.51. That's right, gram or G, grams. So let's draw this. So going to our graph, looking at we can probably zoom out a little bit. Looking to where that point would be. It's a large value. That's one of our big boys. It'll be right here. So remember, this is the actual value. Remember, this point represents the x and y coordinates here and here. This has an x coordinate of 471 and a y coordinate of 1020. The predicted y value would be what we would get on this line here, the line right below it. That would be at 471, comma, what we predicted, which would be 946.49. Let me go in pink actually to make it stand out. 471, comma 946.49 would be this. And the residual will be the difference, will be this vertical line here. It's kind of small. And if I zoom in, so this residual is this difference right here. That's your residual. Remember, think of this as your actual y. This is your predicted y. Actual predicted, actual predicted, actual predicted. So that's how you get that vertical distance. Or that's, basically what it shows, what it means on there. All right, and then the last part, let's go to the part F, where the warehouse is saying they want to offer a supersized box at 600 square inches, and the residual for the box is 1,005 grams. So now we have to actually find what the actual weight of the box would be. So it's kind of working backwards. So we're using our equation again. Residual is equal to actual minus actual y minus predicted y, or in other words, like y minus y hat in this case, and symbols. So we know the residuals. So we're given that the residuals is 1,005. So the left side is that. The y is, what we're trying to figure out, the actual y, or the y here. And let's see what the residuals would be, what the residual will be here. So let's go ahead, let's see what would happen here. I don't know why I put an equal sign for you. 1,000 equals y, actual y, minus the predicted y. Let me put it in pink there, or this. That we can figure out by plugging 600 into our equation for x. So this will be negative 132.1 plus 2.29 times 600. Remember, we're just plugging this x value into our equation for x, and we're going to calculate. We're going to get a value here. Working it, y minus, doing the math, negative 132.1 plus 2.29 times 600, 1241 over here. 1241, well, 1241.9. So we get 1,005 equals y minus 1241.9. So we just solve for the y now. It becomes algebra. We just have to add that 1241.9 to both sides, and we'll get the y. So let's just add this to 1,005 plus 1241.9. And bang, you're gonna get the actual y is 2246.9. That's a big boy. Let me go purple here. Actual y equals 2,246.9 grams. Dang, and there we go.